Hi, this is Arindam from the School of Chemical Sciences, NISER, and a very warm welcome to the lecture series on hydrogen atom problem. This is lecture 5 of the series. In the last 4 lectures, we have slowly developed the theory of hydrogen atom. In lecture 1, we developed the differential equations, which we started solving from lecture 2 onwards. In lecture 2, you solved the angular equations, and we got the two quantum numbers ml and L. We also found that ml or mod ml has an upper limit and which is equal to L as the value. In lecture 3, we solved the radial part. We got another quantum number n, and we found that L now can take only value up to n minus 1. In lecture 4, we normalized the wave functions, and then we got a series of normalized hydrogen atom wave functions depending on different quantum numbers. So this electron in the hydrogen atom can be in any one of these energy eigenstates. Well, it can also be any one of the linear combinations of these eigenstates, but at this moment we are not talking about the linear combinations. We are assuming that the electron is any one of these energy eigenstates. So the lecture 5 that I'm planning to do is that we have to analyze these wave functions a little more. We'll plot them. We'll also take the complex conjugate of these wave functions, and then we'll try to get the probability density of these electrons, which means that we'll try to find out the probability of finding the electron at a particular position with respect to this nucleus. So let's start doing that portion. So before we proceed, I would like to do the following. So if we just look at the total wave function of the hydrogen atom, that can be written in this particular form. We know that we have already did this in lecture 2, that the space part and the time part can be split into two parts, and this is possible because the potential under which this electron is moving is not an explicit function of time. Therefore, the separation of variables between the space part and the time part is possible to do. And then once we do this, the immediate implication that we get is that the quantity capital psi star psi, which is the probability density, is becoming exactly equal to the small psi star psi, which is the space part only, meaning that the probability density is not a function of time explicitly. It means that if we calculate the probability density today and we find something, this probability density is going to be the same tomorrow as well. It is not going to be fluctuating with time. We also know that the psi, nl, ml, these functions can be written in this particular normalized way. I have just given you the entire list of this. What we'll be doing before proceeding is that we'll be not only be happy with the overall normalization like this, where the normalization means this quantity is equal to 1, where the d tau is the volume element, and that is equal to sine squared r squared sine theta dr d theta d phi in spherical polar coordinates. So this whole quantity is equal to 1. This particular thing is true. This means that the probability interpretation is valid. That means the electron is definitely be available somewhere in this world. But before doing anything else, I would like to split this normalized psi function into two parts, where the radial part is also going to be individually normalized, and the angular part, now I'm using the spherical harmonics symbol, this angular part is also going to be individually normalized. What does it mean? It means that these two are going to be simultaneously verified. So the r squared dr, this is the radial part of the d tau, right, r squared dr, that I have taken over here, whereas the angular part, which is the sine theta d theta d phi, that I have taken with this angular part. I can also call this whole angular part together as a d omega. So these two are individually normalized. Now the question is that why do I really need the overall normalized space part to be split into two parts, r and this y, which are individually normalized? That I'm going to explain a little later, but that is going to be useful for us. Now there is a formula for normalized radial functions, and this formula is this one, right? Let me explain this slowly. So the rest of the symbols are already known to you. It's not a problem. Given a particular n and l, this entire thing can be calculated. The only thing which is probably not known to you so far is this particular part. This is the polynomial. It is defined in this way. So L n plus L to L plus 1, this quantity. Now if you remember from lecture 2 and also from lecture 3 that this quantity we defined to be as the symbol rho. So therefore, I can also write down in this way. So this is called the associated Laguerre polynomial, and that is related to the original Laguerre polynomials, which are this one in this particular way. So the associated Laguerre polynomials and the Laguerre polynomials are related this way, where the Laguerre polynomials are defined in this particular fashion. Right? So it looks a bit complicated. So let's take examples. Examples are the best thing to explain something. So let's take a simple examples. So let's take the example of n equals 1 and L equals 0. That is the easiest example that we can find. So let's try to compare these two lines, right? So then we have this -2, same. Now n equals 1, so therefore this is just z over a0 through a2. And this is n equals 1, L equals 0, so therefore a1 minus 0 minus 1, which is 0, so factorial 0 is 1, and then we have n equals 1, and then n plus L is also 1, so therefore this entire thing is 1, and as L equals 0, so this whole thing is also 1. This particular part will remain, and then as n plus L is 1 and 2L plus 1 is also 1, so we get L11 rho. Correct? So the L11 rho is now defined according to this particular formula. This particular formula. So if L11, then we can immediately get that dd rho of 2L plus 1 is 1. So therefore dd rho, and then n plus L is also 1. So therefore L1 rho. Right? And L1 rho, if I just take L1 rho, that is e to the power rho, and it's only one time differential, so dd rho, and then we have rho to the power 1, so therefore rho, and then e to the power minus rho. So therefore this is the situation, and if you just now simply perform this differential inside, we simply get that this whole thing is equal to -1. So therefore L11 rho is -1. So we have to put -1 over here, and if we do this, then we find that this R10 turns out to be this much, right? Now if you just quickly compare the 100 part, we see that this 100 part didn't really have 2 here, rather we had 1 over root pi. Let me see, okay, we cannot see it here. So this way, so therefore we had 2 here in the R10, but in this psi 100 we had 1 over root pi instead of this 2. So this is coming because of the normalization of the spherical part. So let's talk about that now. So the spherical part, now we know that the spherical part, this y00, while L equals 0, ML equals 0, is going to be split into the theta LML 00 and phi ML 0, correct? And we know that both of these are 1. So we have seen this previously, that both of these are 1. So if they are both 1, then if you have to normalize them, then we have to do something like this. So let's take a normalization factor a square, and then we try to normalize the whole thing. So this is again sine theta d theta d phi is our d omega, right, with the angular part, and this is equal to 1. So if we just perform this integration, simple one, we get a equals 1 over 2 root pi. So therefore we get now the angular part, this part is normalized, 1 and 1 coming because of the theta and phi, both are 1 for L equals 0, ML equals 0, that's a different thing. But now this particular portion is normalized separately, and this particular portion is also normalized separately, and when you mix them together, then we get this particular 1 over root pi equation, which is we have already seen that this is the psi 100 equation. So therefore we are getting it now same as this one once we combine these two. So this is the way we can also do another example if we wish. For example, a slightly complex example of 210. So this is the psi 210. It has a explicit theta part, and I can now want to split this whole thing as R21, n equals 2 and L equals 1, so it NL, and then L equals 1, ML equals 0, right? So therefore we want to get these two. So we'll be using the formula again. And if we just plug in the formula with n equals 2 and L equals 1, this becomes the formula, right? And L33 is given by this according to the formula of Laguerre polynomials. If we just do the calculation, I can give you a glimpse of this calculation. So this calculation I have done over here. So if we just do this entire calculation, right, it's just simple step-by-step differentials, nothing else. It's simple. We get finally that L33 is minus 6. So this is the minus 6 that we get, and also this particular factor we get here. This particular factor we are getting here. So the 1 over 266 cube. This particular factor can be written down in this particular fashion is 1 over 2 all root 3. So if we just do everything together, we put the L33 as minus 6. Then what will happen that this minus 6 will cancel with this minus here, and then we have this is equal to 1 over 2 all root 3, etc., etc. And everything if you do, then finally what you get is that R21 is equal to this particular portion, right? So this is the normalized part of the radial equation of psi 210. Now let's go back. Let's go to the angular part. Now we know that the angular part has this theta 10. Now theta 10 is cos theta. We have developed before as well. The theta 10 is cos theta, and we have some normalization constant a that we have to get now. And again, phi 0 is 1. That's not a problem. So we now get we have to solve this particular situation so that we get the value of a square. So if we just calculate this simple integration, we find as a equals root 3 over 2 pi, 2 root pi rather. Then we get this normalized angular part as this one, and then if you combine this with the normalized radial part, right? So this is 210, so I have to make it a 221 here. This is 21 and this is 10. This is correct. So then this combine this, and then this becomes this particular thing. So 1 over 4 then root 2 pi, and then if you compare this with the list that we had earlier, so this will be matching with this 210 is 1 over 4 root over 2 pi and so on and so forth. So this particular, so what is happening is that we have this normalization constant which is split into two parts, right? So we have split into two parts. Now the question is that why you have done this. So the question I have written down over here is that why it is necessary to split this. The necessity is this. So when you will be calculating the probability density, the splitting of two individually normalized part will help us to study the radial probability and the angular probability separately. How? This is how. So the quantity, again I'm bringing to the capital psi again, the quantity psi star psi d tau represents the probability of finding the electron at time t at a space point r theta phi. So we can take a space point here and r theta phi, and we can assume a small volume element d tau, which is given by r square sine theta dr d theta d phi. So therefore the psi star psi d tau represents the probability of finding the electron at time t at space point r theta phi between r and r plus dr, theta and theta plus d theta, phi and phi plus d phi. This particular thing. So it simply means that we have this probability, this one. Now I have already told you that this is simply equal to this, because this time part drops out, so the probability is not a function of time. Now this one is again, I can split, because the psi can be split into r and y, so I can split in this particular way. Now the probability, what will happen is that the probability of finding the electron at r theta phi within the volume element d tau is now this. And now what we do is that if we now integrate over the theta and phi, correct? If we now integrate over the theta and phi, what will happen is that we'll get the probability of finding. So we are now integrating over theta and phi. So therefore the probability of finding the electron at distance r from the nucleus between r and r plus dr for all theta and all phi. What does it mean, all theta and all phi? So if we now let's try to draw a picture. What will happen, so you have a situation that you have this nucleus here, so we go into some distance r, and then an r plus dr, so this is your dr, and then if we have this is in a particular direction, but now this, if we just make this a circle, two concentric circles, well, I'm extremely bad at making the circles, fine, doesn't matter. So this concentric circles, and now you take and you rotate this particular thing about the z-axis, so this becomes a sphere, right? So therefore you get two concentric spheres, one is of radii r, another is radii r plus dr, and this volume within the two spheres, that particular volume is what we are talking about, is that the probability of finding. Now if we just integrate over this, then the probability of finding the electron within that particular the shell that we are going to get, that is called the radial probability, right? Because what happens is that if I have this whole quantity now here, and if we integrate over the theta and the phi, we know that this is just going to be the r square or r mod square, if you call it that way, r mod square r dr, because we already know that the integration over theta and phi, right, will give this whole quantity 1, because I have already worked on the fact that these Rn L and the YLML, they are individually normalized. So therefore the integration over theta and phi will simply make this whole thing 1. So what is left over? The leftover is Rnl mod square or square, because it's a real function, Rn mod square dr, right? So this particular, no, it's not dr, it's going to be an r square dr, because it's going to be it's not a dr, this is going to be r square dr, right? Because obviously the r square will be remaining with this, the sine theta d theta d phi will go with the angular part. So therefore this whole thing is going to be an RL square r square dr. So therefore what happens, this particular quantity, this PR, right? So this is an r square will be here and r square has to be here. This quantity is known as the radial probability density. So I have written down a few of the first radial functions, the normalized radial part of the wave functions, and these are of these forms. So let's have a better look at them. So what you find is that these ones where L equals 0, so these ones are known as the s orbitals, like this is an 1s orbital, this is a 2s orbital, right? This is a 3s orbital, right? This is a 2p, and then this is a 3p, and then this is a 3d. So these are the different, these are names that generally we give. So we find that whenever it is an s orbital, this particular these radial functions are not 0 at r equals 0, right? We do not have this. So for example, this 2 1 has this factor, and therefore at r equals 0, the entire wave function is, this entire radial part is 0. Similarly, for even this one, when 3 1 or 3 2, we have an r or we have an r square. So these terms make this 3 1 or 3 2 at 0 at r equals 0. So therefore, each of these 1s and 2s and 3s and 4s or any ns orbitals, right, the radial part is not 0 at r equals 0, and it has a very profound implications. Later on, if you study the different hyperfine interaction between the nucleus and the electron, you will find that the s orbital electrons, they take part more into this hyperfine interaction. The Fermi contact interaction, for example, I just remember one example, Fermi contact interaction. So these are primarily be taken part by the s orbital electrons, because their wave functions are not zero at r equals 0, and therefore we'll be getting appreciable a probability of finding these electrons very close to this nucleus. So if we just try to plot it, this R10 is a simple exponential drop, right? So it starts from certain vector. Forget about the y-axis. Let's take an arbitrary axis. So therefore, this one, we know that when R becomes, so let's take Z equals 1, so hydrogen atom. So then when R is equal to something like either 3a0 or 4a0, this exponential minus e to minus 3 or minus 4, there will be 99% drop from the original initial value, whatever it is, an arbitrary axis. So therefore, if you just take R in this axis in terms of a0, so therefore 1, 2, 3, 4, 5, 6, 7. So 1, 2, 3, 4, 5, let me 5 is 1, 6, 7, 8. So therefore, this wave function is going to be a simple exponential drop like this. So this is going to be an R10 function, which is non-zero at r equals 0. That means at the center of the nucleus it is non-zero. But now when we'll try to find out the probability density, right? So when you will call the PR for 10 dr, that is going to be this R10 mod square multiplied by r square dr. Right? So we'll be plotting this particular quantity. So R10 mod square r square. So R10 is a real function. So therefore we have to simply make it a square. So therefore the PR10 is going to be Z over a0. We can put Z equals 1 if we want. This is cube, and then we have a 4, and then we have exponential minus 2 times z times r over a0, and then we have an r square, right? So this is our PR. This is the probability density along with this r. If we multiply with this dr, then it becomes the probability of finding the particle between r and r plus dr for all theta and all phi. That means between the shells created by the two spheres of radii r and r plus dr. So this is the probability density. Now we know this is an r square. So therefore, if we just try to plot it, right? If you just plot it, this r square is going to be a parabolic function. So it should start going up, correct? And but then after r becomes appreciably large, this exponential drop will make it drop like this. So ideally this is supposed to be this way, but no, this is an exaggeration. This particular rise and exaggeration. If we really try to see how this particular thing looks like, it is the picture is of this particular way. So therefore this is the picture for n equals 1 and l equals 0. So therefore this is R10 mod square r square. So therefore say this is PR10 is equal to this. So this has been plotted this way. Now I'll be explaining what this dotted line is all about, and whatever this particular triangle is all about. But the idea is that this particular shape is like this. It rises sharply and then goes down at about r equals 5a0, right? So therefore the x-axis is with respect to a0, z equals 1 anyway. So this particular one. So this is the quantity that is being plotted there. So although the wave function is not 0 at r equals 0, but the probability of finding the electron between r and r plus dr goes to 0 when r goes to 0 because of this particular factor. So let's do some more math and try to find out that in this particular distribution, so this is basically a probability distribution. So therefore now the electron can be anywhere between about say 0 to all the way to almost like 5a0. So this entire region is available for the 1s electron, but now let's try to find out exactly where the probability is maximum. So this is the dotted line shows basically the probability, the position where the probability is maximum. How to get that? It is simple. All you have to do is that you have to take this dp10r and with respect to dr, and this should be equated to 0. So if we do this, we find that this is equal to, so this gives me 2r e to the power minus 2zr over a0 minus 2r square z over a0 e to the power minus 2zr over a0. This is equal to 0. And we get two solution from here. So this gives me 2r to the power minus 2zr over a0, and then we get 1 minus rz over a0, and this is equal to 0. Right? So therefore we get two solutions. One is r equals 0, and we get r equals a0 for z equals 1. Right? So if I put z equals 1 here, we get from here one solution, r equals a0, another solution is r equals 0. So we know that both r equals 0, so r equals 0 also it is flat, because it's a parabolic function here at because of this r square, but this is not the maximum, correct? So therefore this is not the correct solution for the maximum. The maximum solution is this. So therefore we find that for 1s electron, the maximum probability is at a0. A0 is, that means so the maximum probability for, so the electron in 1 0 electron, correct? So when it is an r10, so this 1s electron is maximum probability at a0, which is the first Bohr orbit. So therefore, the Bohr's theory comes alive again, that we find that although the orbit picture is out now, so in an orbit picture, the electron is restricted to a particular distance a0, the first Bohr orbit, and the electron is not allowed to move either slightly further away from that, or it cannot come even closer. But here, that is not the situation. In the Schrodinger picture, we find that the electron is very much allowed to move a little bit about its maximum position, but this position is, the maximum position is coming to be equal to the first Bohr orbit, which is nice, which gives some credibility to the Bohr's theory. So the next thing that we'll be like to do is we'll be trying to find out the average position. So the small triangle here, the small triangle says that average position. So this is the most probable position, which is the maximum of this probability, and now we'll get an average position. So how to get the average position when you have a certain probability distribution? That's pretty simple. So let's try to get the average position, and then this is average position r bar is given by this integration r equals 0 to infinity r, the value of r, times p of certain nl. It doesn't matter whether it's a pr dr dr certain nl. So therefore this is going to be the average position for a particular NL. So what we do now is that we will be plugging in the P10 here, right? PR dr. So this particular thing, and this comes out to be equal to 4, and then we have z over a0 whole cube, and then it's 0 to infinity, and then we have r cube e to the power minus alpha r dr, where alpha is equal to 2z over a0, right? So we can do this this integration by using the integration over integration by parts. Several steps it has to be, right? But this ultimately this whole thing is going to be equal to 6 over alpha to the power 4. That is going where alpha is given by this. So I can simply take this thing as 6 over a0 to the power 4. Now is 16 coming, and z to the power 4. So this whole integral is this quantity. So therefore the r average for 1 0 comes equal to 4 times z over a0 whole cube, and then we get 6 a0 to the power 4 and 16 z to the power 4, right? So this comes to be is equal to 3 to a0 for z equals 1. So if we take the hydrogen atom z equals 1, then this whole thing comes out to be 3 over 2 a0. So this is exactly what has been plotted here, right? So the average is 1.5. So this is 1 a0, right? This is first boron. This is the 2 times a0. So therefore the average position is 1.5 times a0. So this is the average position. So we have got this average position. So similarly, we can have different radial probability distributions, right? So n equals 2, l equals 1. Now the thing is that we see that this particular thing has this particular feature, that it has started going, then comes back to 0, and then it goes up. So let's see why this particular feature is coming. So this feature is coming from the radial part again. Right? So if you look at this thing, so this is definitely not 0 at r equals 0, but it has a node. So this quantity, when this quantity is 0, then we get a node, and that node directly come at, so therefore this whole thing, this node will be coming at when r is equal to 2 times a0 over z. Now, well, z can be 1 for protons, so therefore r equals 2a0, we have a node. So therefore if we try to plot it, we can plot this. So let's plot that particular function first. So let's try to plot it. So we have something like this. So 1 2 3 4 5. So therefore at 2a0, r equals 2a0, correct? So r equals 2a0, we should have a node. So therefore it's going to be something like and then it is going to be like this. So therefore the r20, so this r20, this function has a node, and then it goes right. So therefore you have a positive part here, the wave function is positive up to this, and then it becomes a negative here, right? So therefore when you plot this this particular part, this particular part is coming from this part, and then this entire big part is coming from this whole thing, right? So often you can call this is the positive part, correct, and this is the negative part, although the probability is never negative, probability is always square, correct? But often this is given a positive and the negative sign on the probability part as well, with this node here, and then this particular part, so sometimes it is given some color as a blue and red, and that is this plus minus is nothing to do with the probability. Probability is always positive, but that is to do with the actual wave function, when the wave function is be positive and negative this way. Similarly, if we look at the for example the 3-0, then we find that we have a polynomial of order 2. So therefore we'll be having two solutions when this particular polynomial is going to be 0, right? So therefore we should have so therefore we should have two different places that this r30 is going to be a 0. So it will have two nodes, and that two nodes are reflected here. So if we just take if we just take the R3 n equals 3 and L equals 0, so which is basically the 3s, it has two nodes, one is here, another is here, right? Even if we do, and then how the plus minus is going to be plus here and it will be minus here and it will be plus here. So basically if you had to draw it, right, it is going to be something like, it is going to be kind of like this, coming here and then it is go up and then it is like this. So therefore you have a positive here, then you have a negative here, then a positive here. So you have two nodes, one is here, another is here. So there are two nodes. So this is the radial part is going to be, we just plot it. And then this is going to be the corresponding radial probability density. So this is the radial function, this is the radial probability density, and so on and so forth. So this is a simple one. When you do not have any angular part, then this is how easily you can draw any of the radial probability distribution or the radial functions. Now let's talk about if we have really the angular part, how that particular thing can be tackled, right? So the angular part comes from the y part that we have defined. So the y LM or LML theta phi. This is given by definitely the theta LML theta and then a phi ML phi. So this is the angular part of the equation. Now we know that the solution of this angular part is e to the power plus I ml phi. This is the functional form for the phi part. So therefore, when you do an YL ML star YL ML, what we get is we get a theta part definitely theta star L LML and theta L ML, but the phi star phi becomes 1. What does it mean? It means that the angular part, or in general the entire total probability distribution of hydrogen atom is not dependent on phi, right? So all this probability distribution, all the we call it the atomic orbitals, right? There's this probability distribution, the probability gas, right? We call the three-dimensional probability distribution is the orbital. They are all symmetric about this phi axis. The phi axis means that it is symmetric about the rotation along z axis, the phi. So therefore, if you just try to draw the the axis, right, the 1s and 2s, everything is definitely it doesn't have any theta dependence, it doesn't have any phi dependence, because it is only the r part. So therefore it is really spherical symmetric, right? We have already seen this particular thing. So if you have an 1s for example orbital, right? So you can go any direction, you get basically exactly the, so you get this direction, right? You basically get the same distribution. It just goes up, down, and then it is slowly going down like this. So therefore the density, so you have a sphere, in 1s probability distribution is basically a sphere, but not with uniform density. The density first goes up and then the density goes down. So but this is a sphere. You go any direction of any theta and any phi, you always get this particular distribution. But that is not always true for all the functions, but nonetheless each and every probability distribution is independent of phi. So therefore you have a absolute rotation symmetry with respect to this phi axis, this particular rotation, right? So that is true, but this theta part will give certain distribution. For example, so let's take this particular example, like 210. It has an explicit cos theta as a function, or maybe we can take this one which has a sine theta function, although it has this particular phi part, but the moment I'll be doing a modulus square, this will drop. So therefore this is not going to be a function of phi, but theta or cos theta or sine theta will remain. So if what happens if we have a cos theta, right? So then what we have to do is, if we just simply take a z-axis, from that it is the theta is measured, right? So this particular thing, and then if we try to plot in a particular direction, right, for a particular theta, if we try to plot this quantity theta star theta, right? So for this particular thing which has a cos theta as the theta part, so theta star theta is simply cos square theta. So if we just plot cos square theta for a different theta, and then what will happen, that it will get something like this. So cos theta is maximum when you have theta equals 0 or theta equals pi. So you get something like this. This is the one. So when it is when this particular angle is 0, you have maximum 1, and then it is dropping, and then as theta is exactly 90, correct? So therefore this is going to 0. So therefore this particular direction, this is the value, this is the amount. So if we just keep plotting those, we get this particular thing. Again, when theta becomes 180 degree this way, again it is maximum because it is -1. But if we just square it, cos square theta, it becomes 1. So therefore, as theta spans from all the way to 0 to pi, correct? And if we just simply on that particular line, if we just plot, take the point which is proportional to some cos square theta, we get this particular contour. And now, as we already know that this is it has to be independent of phi. So after we get this particular picture, we have to make a rotation about phi to get the actual orbital shape of the theta. Right? So you basically get, if we just do this, then you get, this is 0. So you get, right? So this is the. So this is the three-dimensional, I hope I could make it a three-dimensional balloon, correct? That is coming because of this particular shape first, which is a cos square theta shape, and then the cos square theta shape has, now it is just a two-dimensional picture, and now that's two-dimensional picture, if you rotate along Z, it will become a balloon, right? So that is the situation, that this is our n equals we had 2 and L equals 1. So we call this a 2p orbital now, and L equals 1, but this one is ml equals 0, right? So we have taken the ml equals 0, 1, 2, 1, 0, which is cos theta. So therefore I call this as a 2p0 orbital. Now how does this look like? So we already have a 2, 1, 0 radial function. So if I just show you the radial function, 2, 1, 0. So this is the 2, 1 radial function. We had a certain at r equals 0, it is 0, but then we have an exponential function. Therefore we have you have an r goes up and then it comes down. So let me draw it. So here the function r 2, 1 is of this particular form, so it goes up and then it comes down, right? So this is the R21, and it has this particular angular dependence. What does it mean? Let me talk about this together. What do you mean by this angular dependence and this one? So we have, for example, this picture, right? So if I just take in this direction, for example, we get this entire thing, right? So therefore in this particular direction we get the entire thing. But if I take in this particular direction, right, if I take this direction, well, in this direction we get this same thing but a much smaller amplitude. Now if I get in this direction, so I get 0, nothing. Now if I take in this direction, right, again I get a little bit, and if I take again this direction, right, if I take this direction, then this one is again full. right? So this is how the probability distribution will be done. So that as a function of r, you will get this particular probability distribution, right? Because we have the radial part, radial PR, dr, this form. But then which direction you will go. So you will get r distance from the nucleus, that is okay. But whether you will go in this direction or you will go to this direction, if you have a theta part explicitly, then that will not be same in which direction. So therefore, if you get in this direction, in this particular wave function, you get a much better probability of finding the electron. It is a large probability is here, and then the probability goes down. But in this direction, well, the probability is zero to start with. You will not get anything on this particular. So therefore, this is a node. So this particular point is a node, and you have one probability on the top and one probability. So therefore, you have a nodal plane. Now you have a nodal plane and that particular thing. So this lobe is on top of the nodal plane, this is at the bottom of the nodal plane, and then what happens, you know that cos theta, as it goes from top to bottom, correct? So the cos theta, as it goes from 0 to 90, it is positive, and then 90 to 180 is negative. So therefore the wave function is going to be positive on top and the negative and the down. So often what we do is that after we write down this, we call this is a plus and this is a minus. Although we know that probability can never be plus or minus, probability is always positive. But as the wave function is positive in the top and the negative in the down, because you have a cos theta term, right? That is why we often call this as a plus and minus, right? Now the question is that another one if you just look at the 2, 1 plus minus 1, which is a sine theta. Now the thing is that again phi is there, but the mod square is independent of phi. So therefore the 2, 1 plus minus 1 is also going to be symmetric about the z-axis. But any chemistry student will say that, well, that is not true. We have, this is our P2P0, or which is also called something 2PZ, because this is the z-axis. But also we know that the 2px and 2py are there. So therefore you have a 2px like this, and then we have 2py like this. These are not symmetric with respect to this the rotation. What is happening? The thing is that the 2p plus 1 and 2p minus 1 are really symmetric. But if you take a linear combination of these, and then you get 1 over root 2, then you will find that these are becoming either the px and py. For example, you have the plus and minus 1, this is a plus and minus 1. So if you take the plus and minus 1 combination, correct? So if you take something like e to the power I phi plus e to the power minus I phi, right? So this is your 2 times sine phi, right? So therefore your 2px is going to be a sine theta sine phi dependence, and a 2py is going to be an sine theta cos phi dependence, and therefore you'll be getting them that at theta is going to be theta 90 degree maximum. That is why you will be getting maximum in the xy plane. Here the xy plane was 0 because it was cos theta, but here it is a sine theta, right? So you have a sine theta here. So therefore you have, as you have a sine theta here, so you have maximum in the xy plane, but in the xy plane also it is not symmetric because you have a cosine phi and sine phi. So therefore 2px, which is 2p plus 1 plus 2p minus 1, this one is along the x-axis because of the phi equals sine phi. This is going to be py and this is going to be px. So the cos phi is a px. So therefore you have along x-axis, and then the py will be along the y-axis. So therefore these are the different things that we can do, and that is how we can draw the different orbitals. So this is more or less whatever I would like to talk about the hydrogen atom problem. So after this long 5 lectures, I'm concluding now this particular chapter. The next chapter that I'll be talking about, maybe it's going to be on angular momentum. I'll be starting from the hydrogen atom. I'll take certain cues from hydrogen atom, and then I'll introduce the angular momentum. In fact, the function that we have introduced in this particular video, that LML correct? The spherical harmonics, this is a theta phi, correct? This is the important part. So this will come in next two chapters. One is going to be the chapter on angular momentum, another is going to be the chapter on rigid rotors. Both of these will have this YLML part, right? So we'll be taking something from this particular chapter, and then we'll go to the next chapter. But let me conclude this hydrogen atom chapter here. I'll see you in the next chapter. Bye bye.